Hi everyone, welcome back to the Astro Imaging channel, and in case you haven't heard it 100 times so far, I hope everyone's having a good start to the new year. Notwithstanding the torrential rain we're having out in the West Coast for all us West Coast images, so if I can say just boo-hoo, boo-hoo. The good weather will be back. We will have clear skies eventually, but I digress. So this week we have Manny Leinz from talk to us about exoplanets. We've had a few talks about that, but it's always a fascinating thing because in our naivete, I think some years back, I always thought, if you get a powerful enough telescope, you should be able to just see these little planets up there. But turns out we can't do that. Let me adjust my mirror. And Manny's going to talk about all the different ways that you can detect exoplanets, and I think you're going to talk some about how if you want to get involved in it as well.
Yep.
Because I think all of us can, if we have an interest, want to go to a star, which Manny will point out how we can find that star, and we can see if there's an exoplanet, or at least reinforce some of the data that's out there already on exoplanets, which is all worthwhile if you have telescope time. I want to spend just a couple of minutes on our calendar, because our calendar is looking a little bleak. I'm not going to bring it up, but so we have Manny this week, and now on the 18th we have Warren Keller stretching in PixInsight. Now, if you haven't gotten the new stretching routine in PixInsight, you definitely need to get it. I can't remember its name, but it is certainly worth the time. And after that, we have Mike Cranfield on Pixel Math. Mike has lots of great utilities, which I think we all use. And that's February 1st, which, by the way, is my birthday. So if you want to send me a birthday card, I don't know, just send it to us. After that, we have all open dates. So we need presenters. We always do need presenters, but now especially we want to keep the Astro Imaging channel live and well, and we need more presenters. We're doing 2 shows a month. So 2 presenters will fill up another month. If you have an idea and you're doing something interesting that's unique to your setup, let us know. You can be part of the Astro Imaging channel. Send a note to contact at the Astro Imaging channel. You can see it on our website, theastroimagingchannel.org, and someone will get back to you. Be a presenter, be part of our show, and help us. Now I kind of sound like the PBS when they're fundraising, but we're not asking for money. We're just asking for a little bit of your time and effort. So I'll have Manny introduce himself, and I will turn the show over to you. So please go ahead.
Yeah, well, thank you, Eric. Yes, I'm Manny Leinz, longtime amateur astronomer. A little more recently got into Astro Imaging, and then literally just 6 months ago thought I would take a crack at exoplanet imaging. And so yeah, that's what this talk's all about. So this is a very much a beginner's guide provided by a beginner. So maybe that makes it better, so that I won't be talking over anybody's head. Please feel free to ask questions along the way. I'd be happy to answer any questions that you have. And I guess with that, I should launch into it.
Yeah, you can go ahead and share your screen.
Okie dokie. Oh, wait. I was doing so well until just now. There we go.
We're going to do your entire screen.
There we go. Close the little thing and go here, and we go there. Can everybody see that?
Yes, we're good.
Okay.
You're good.
All right, onward. Okay, so this is kind of a little outline of the presentation. I'm going to talk a little bit about just what exoplanets are. I think most of us understand kind of top level, but we'll get a little bit deeper. We'll talk about can I really contribute useful data? And then, spoiler alert, the answer is yes, absolutely, you can, whether or not you have a telescope. We'll talk about how you get started, the equipment that you need, and at the simplest level, the equipment you need is literally a computer and an internet connection. So so it's pretty exciting because you can contribute at all levels. We'll talk about what resources are available, and there are thankfully a lot of tutorials, a lot of good software scripts and data available to help you along the way. And then finally, I'll talk to you about kind of my lessons learned in the first few months that I've been at this, and I think that'll be instructive for folks that want to get started. So Exoplanets 101. So exoplanet is short for extrasolar planets. In other words, these are planets beyond our solar system, and they, by definition, are below the limiting mass for thermonuclear fusion. In other words, they're not brown dwarfs. They're not failed stars. They are more like Jupiter or super Jupiter or sub Jupiter class objects. They are, by definition, orbiting stars, orbiting brown dwarfs or stellar remnants, and as I mentioned, by definition, beyond our sun. So those of us who've been around for a while will remember the very first exoplanet discoveries back in 1992, where we had a pulsar that was discovered. I'm sorry, not the pulsar. Two planets orbiting a pulsar were discovered by these two gentlemen, and since then there have been a lot more. This B and C is the nomenclature that persists today. The implicit A is the star, the B is the first planet discovered, and then the C would be the second. And in 1995, we had 51 Pegasi B, and this was the first planet discovered orbiting a sun-like star. So what I'm going to do right now, I'm going to take just a moment, because if you notice this in the lower right-hand corner, I am using LibreOffice, and it has a really annoying habit. I tested this just before I came in, but I'm going to close this presentation with apologies to everyone. I'm going to now reopen it again. And if it doesn't work this time, I'm going to switch over to a PDF. All right, let's see if this is going to work now. Okay, there. Okay, onward.
So weird.
It's so weird. Yes, I was editing text and then realizing that editing text didn't help a lick. So hopefully it won't return again. Okay, so how do we detect exoplanets? There are lots of different ways as it happens, but the two primary ways are what are called the radial velocity method. You might also notice the Doppler method. So here's a situation where a planet orbiting a star is actually causing that star to wobble. And that wobble in and out, if you think about it, slightly changing the redshift of the star, is going to move the star spectra back and forth as the planet goes around. And so we're indirectly detecting the planet by its effect on the star's motion, the star's position. The second major method, which is actually has been used to discover more stars than the radial velocity method, which is called the transit method. And here we're actually looking at the dimming of the star's light due to the passage of a planet in front of it. And so I think when you heard, if you a couple of weeks ago tuned into Brian Kloppenborg's presentation, he talked a little bit about this and showed a graphic where the planets are, if the planets are larger, you're going to get a deeper transit. If the stars are smaller, you're going to get a deeper transit, etc. But this is a method that is used primarily by us amateurs. And we're going to talk a lot more about this in the coming slides. There are other methods as well: pulsar timing, gravitational microlensing, astrometry, direct imaging. I'm not going to talk about these other than just to show you a chart. And so this kind of shows the amazing progress since 1992, when that first planet was discovered, and the kind of almost exponential growth in discoveries. We're up now to over 6,000 exoplanets discovered. This was as of the 10th of October of last year. And so here you see the various different methods. And here's the transit method in purple. So you can see that really does represent the lion's share. And then second, of course, is radial velocity. And then the rest of these methods all are kind of a rather, make up a rather small fraction. So types of exoplanets. We have kind of the holy grail here are the terrestrial planets, and I don't know that we've discovered any of those yet. But most of what we're discovering nowadays through satellites like TESS and others is these Neptune-like or gas giant stars. They're just fundamentally easier to detect because they're larger and they provide a bigger signature, whether it's the transit or radial velocity method or others. And for us, it's the gas giants that are the closest to their stars that are the most likely common targets for us amateurs. And the reason for that is because it takes time for these stars. If you imagine a transit in front of a star, of course the geometry has to be right. The orbital axis of the planet has to be aligned with our line of sight, otherwise you don't get a transit. But you'll see here these the transit discoveries. You'll notice here this is orbital period on the x-axis. Most of these are down in the even sub-day. So you imagine a planet whipping around its star where its year is less than an Earth day. And most of the transit types are down, down 10 days. If you put a distribution here, you'd see that probably down here in the 1 to 10 days is kind of the average for transiting. Radial velocity is spread out a lot more. We are able to detect the longer period ones, and then you see the others here, the really long period ones that detected by imaging methods and others. And I like this here for reference. Here are our solar system objects. So here's the Earth in terms of its mass and its orbital period: Venus, Mercury, Mars, Jupiter, Saturn, Uranus, Neptune. So kind of shows you that in terms of Earths, we really haven't. There's no discoveries around Earth here just yet. Okay, so how can we contribute to exoplanet science? This is really what this is about, right? If you're going to take the time to point your telescope at these planets and try to collect some data, you want it to be, or at least I want it to be of use. I want it to be to advance our understanding of these planets. And thankfully, there are lots of opportunities for us to help out. So I mentioned before that if you don't have a telescope, it's not a problem. There is a program called Planet Hunters TESS, where you are actually looking at existing light curves from TESS, and this is the Transiting Exoplanet Survey Satellite, which this is what it looks like. And it was launched in 2018, completed its primary mission in 2020, but it is still operating. And it has discovered thousands of exoplanets, many, many more than what was defined as mission success. There's also Planet Patrol here, which does similar things, but it's looking in particular to weed out false positives, things such as eclipsing binaries, variable stars can masquerade themselves, or just close double stars can fool the satellites and look in the data as if they are exoplanets when they're really something else. And so there's an opportunity used by Planet Patrol to where you can look at some of this data and help weed out the non-exoplanets. So for both of these, all you need is a computer and an internet connection, which is pretty cool. That's probably a great way to get started. If you have some equipment that you can put to use, there are other opportunities. There is the Test Follow-On Observing Program, which is a collaboration between NASA, MIT, and then the Harvard Center for Astrophysics, I believe. And so here what you're looking at is candidate exoplanets. So these are ones that are not yet confirmed. So you need a telescope, you need a camera, you need, they're requesting an image scale of less than 1 arcsecond per pixel. And you're going to need precision guiding. So you need a guide scope, guide camera, etc. And critically here, you need to get approved. So they don't just take anybody on this one. So this is probably not where you're going to get started. There's also the European Space Agency has what they call ExoClock, which is monitoring known planets in advance of their 2029 aerial mission. And here, once again, you need a telescope and a camera. And by the way, on all of these, I have the last page of my presentation has a list of resources. The resources can also be found in the description below the video, and those are clickable links, which makes it a little bit nicer. So there's a whole bunch of them, and that'll help you get with any of these programs if you want to get started. And then finally, there's Exoplanet Watch, and I'm going to talk more about this. This is through NASA JPL, and this is what I've been contributing to up to this point. I'm looking to get involved with this hopefully shortly. Okay, so Exoplanet Watch. So here what we're dealing with is known exoplanets, but we're trying to refine the transit event times for known planets. So I think Brian Kloppenborg talked about this as well. Here what we're trying to do is save basically imaging time on large space and ground-based telescopes. They really want to nail down these transit times, the ingress and egress times, so that they don't have to you can think about putting guard bands around the transit, so they want to make sure they don't miss it. And some of these transits can move around a little bit, especially if it's a multi-planet system. So what we as amateurs can do here is help nail down these transit times, get better precision, and so allow the professional instruments to not have to waste time because they're not sure exactly when a transit's going to happen. And then there's also an opportunity to discover new exoplanets. So you can sometimes infer the existence of an additional exoplanet around a host star. And this, as I mentioned, if the transit time is moving around a little bit, that is a clue that there might yet be another planet there that is disturbing the one that's the known planet. And also we can confirm new exoplanets. So here we're making transit measurements of candidates. This is more of the TFOP program, but also Exoplanet Watch can help here. And then also as sort of as a corollary, monitoring stellar variability. So brightness changes on the host star that are caused by dark spots or regions, light regions called plages. I learned that during this process. And so if you remember Betelgeuse, that interesting dimming that we had some time ago was due to a cloud in the atmosphere of the star. So it's also an opportunity to catch these sorts of things. So there are a number of ways to participate in Exoplanet Watch. So what you can do is process previously collected data. So this is where someone else has collected the data. If you send an email to Exoplanet Watch, they will send you a data set, and you can go back and analyze that data and then submit your results to the Exoplanet Watch team. Or, and this I find this is very cool, you can use micro-observatory remote robotic telescopes. So here's an example of one. I think this is a 4 or 6 inch telescope. There are a number of them around the world, and you yourself can select targets and control the telescope via the web. which I think is just kind of an amazing thing, that they will let almost anybody go run these telescopes through the web interface. And then once you've collected the data, you can go download the data and process it on your own computer. So I've not tried this. It looks, if anybody has tried it, I'd be interested in hearing your experience, because it just seems very cool to me. And then finally, and I'm going to talk the most about this, you can collect and process data from your own system. So what you need here is a polar aligned mount and telescope. You really want to have a cooled monochrome camera. The color cameras have that Bayer matrix on the front, and that means you're going to get variable responsivity in the red, green, and blue channels, which you really don't want. If a star drifts, say, from a red channel to a green channel, that's going to cause a shift in the ADU counts, the output, and that's just. I've heard that you can deal with color cameras, but it's definitely far better if you have a monochrome camera. And then you really want to be able to have an auto guide capability, guiding. You want to have that star move as little as possible across the focal plane. Every pixel on your detector has a different gain, and so you really would like to minimize the number of pixels that target star moves across, because any change in response in the ADU counts is going to potentially swamp your target signal from your target star. So you don't want that. And it's definitely better to have a permanent observatory, just from the standpoint of not having to set up and polar align and all that kind of stuff. It's not essential. If you're dedicated, you can set this up in your driveway. And further, you don't have to be, it's better if you're at a dark site, but you don't absolutely have to be at a Bortle 1, 2, or 3 site. You can do this from a moderately light polluted location, as long as your star that you're imaging is bright enough. This is an image of, this is my telescope, and I'll talk a little bit about that in a bit. So
could you hold on for a minute, Manny?
Sure.
There's a couple of questions come up from me.
Okay.
When you were talking about the TFOP test program,
yes.
You mentioned that you needed precision guiding. When you say that, you mean just good guiding? Like, does it have to be any better than we've got already?
Yeah, I think good guiding probably would have been
Okay.
a better terminology to use.
Okay.
I've been reasonably successful, and actually I've realized through my imaging I've done to this point is that I really need to touch up my polar alignment a little bit, because I'm getting more drift than I would like, and I'm getting a little bit of field rotation. And so so yeah, as soon as I get up there next week, I'll be up at my observatory, and I'll be, one of the high priorities will be getting the polar alignment touched up. But yeah,
if you don't get flooded out up there.
Right, exactly. Yeah.
It's been really bad rain here in California, and that's
yes.
where Manny's observatory is.
Absolutely.
North Central California. Anyway, the when you say you can get exoplanet watch data.
Yes.
Data sounds like numbers. Are we talking numbers or photos, or what are we getting?
Okay, they are images. Yeah.
Okay, so we'll get their images, and we're going to apply the analysis like you're going to show us a little bit later, comparing stars to stars.
That's right.
Okay. Okay. That's all the questions. I want to remind people, Manny's already referenced it, but our last presentation, we had a very extensive presentation about variable stars, and there was a lot of stuff about exoplanets. So if you're interested in this stuff, the AAVSO, you want to go see that program from the last time we had a show. And I think that's it for now. Don't forget, out there, if you have any questions, type them into your comment section there on the YouTube, and we'll get them to Manny. Okay. Thanks, Manny.
Sure. Okay, so if you remember, I talked earlier about the small robotic telescopes, and this is the calendar that you go when you log into the website. You'll see here here's schedule target. So you can, for example, what's today? Today's the 4th. So WASP 12 is a good target for tonight, and you could literally click on this. It would give you the ephemerides for this target, and then you could go here and you can control the telescope and literally go here through this interface and collect your own data, your own images from the telescope, download those images, and then process them by methods that I'll talk about in a couple of minutes here. So yeah, like I said, this is just super cool. And the thing you'll notice here is that there's a whole lot of transits here. That's like not quite here every night, but I would say comfortably half of the nights here there is a target. So not good now with all the clouds and the rain, but yeah, so there are lots of opportunities for imaging. Okay, so if you're using your own camera, this is my observatory and telescope here. So I have I'm in Mariposa, which is, for those that don't know, that's a small town west of Yosemite National Park. Very pretty up there, about 3,000 feet elevation. I have a Celestron Rasa 11, which you see in the picture here, an Ioptron mount, and just recently upgraded to a Player One Zeus 455. That's a full frame camera. And then I use N.I.N.A and PhD for PhD2 for imaging guiding. And the observatory is fully remote capable. And if you're interested in how this is done, I use some open source software called Home Assistant and a Raspberry Pi computer to control the observatory. And I think in the links in the description, there are a couple more videos on the AstroImageJ channel where I talk about, and go into a lot more detail on how I did this. But in any event, like I said, I use N.I.N.A. There is a very cool and useful plugin called Exoplanets. So those that are familiar with using N.I.N.A, you literally can download this plugin for N.I.N.A. And what this does is you basically type in the name of the exoplanet. It will give you the ephemeris and load it into the advanced sequencer for you. There is, by the way, an exposure calculator that is part of the plugin as well. I have used this and have found that it doesn't do too good of a job of calculating exposures. I submit that I may be using it wrong, but what I end up doing is take snapshots prior to the expected transit time, and then I basically manually adjust the exposure, keeping in mind the fact that if the target is low on the horizon, it's going to get brighter as it gets higher. And so you got to make sure that you don't saturate, and that so you want to have a good signal to noise ratio. I'll talk more about this later. You want to have a good signal to noise ratio, typically 100:1 if you can. And you definitely do not want to saturate the target star, because you are not going to see that transit if the star is saturated. The other thing I do in N.I.N.A is I set up a custom exoplanets profile. So I have a profile in N.I.N.A for astrophotography. I have another one for exoplanets. And that helps me to not forget that I really want my files to be saved in FITS format, because that's what the processing tools use. And I really want my target name, the region of interest, and we'll talk more about why I use region of interest in a minute, the exposure time, and the gain. I really want all these things in my file name, because they're going to become important later when I do processing. Okay, so how do you get started? Well, the first thing I do is I go find a target. So there is a very cool tool, and again, Brian mentioned this in his talk, called Swarthmore Transit Finder. And here's a little screenshot of what it looks like. This was developed by the Swarthmore College in Pennsylvania, the Department of Physics and Astronomy. This is, to me, the go-to tool for target selection. You can customize your target list by what your equipment is capable of. So, for example, transit depth, how long the transit is, the magnitude of the star, how high the star is above the horizon. All these things are important. You don't want to have the star set in the middle of the transit. You don't want to shoot for a star that is where the transit depth is just too shallow to be able to see with your equipment. And you want to have a sense of how long this thing is going to be. Are you going to have a meridian flip? Is it going to be right in the middle of the transit, or worse yet, right during ingress or egress? And then it provides key information. It links to online databases and finder charts, and links to the Exoplanet Archive, Exoplanet Watch, and TESS databases. So one of the things you can do here is you can click right here on an annotated chart, and it will pop up this finder chart. So here you see this is 10 arc minutes on a side. There's our target right there, this little triple system. And it'll draw a ring around it. This is super helpful when you're taking an image and you need to find the target star in your image. Is really helpful to be able to compare your image with this one here to confirm that you have the right star. Because believe me, if you pick the wrong star as your target when you're post-processing later, you're just going to be really disappointed. The other thing you can do is you can, and I do this also, I have a spreadsheet that I keep. And so all this data here, you can have output as a comma-separated variable file, which I then pull into my spreadsheet so that I have it for later. And then also it can be an HTML format, which is what you see here. And then you can also set up a custom URL. And so that will keep your site information and lots of preferences, say transit depth and minimum target height, things like this, so that because otherwise, if you don't do this, you get a really long list, and it takes a while to go through the list and decide which ones of these you can actually image with your system. Okay, so over to N.I.N.A. Here's a screenshot of what it looks like when you're set up to do a transit. So here, in this case, my target happens to be TOI 5205b, the first target on this star. Now, TOI is a target of interest. This is the TESS target of interest. And you can see here, this is the Exoplanet plugin. I have plugged in the target here, and boom, it has showed me that the right ascension is 1 hour, 4 minutes, 44.39 seconds, etc. Declination. It shows me where the ephemeris came from. Here's the magnitude of the star, the depth of the transit, and this is in what's called millimagnitudes. So this is 16 parts per thousand, or 1.6%. So this is this is definitely reachable with my system. I've gotten successful transits, I think, down to about 0.5%, where the star is dimmed by about 0.5%. This is about 1.6%, so not too bad. Anyway, so there's I'm not going to talk about all these different things here. Let me go on to the next slide. Oh, one more thing here. You'll see that in this case, you could see that the transit is going to occur right centered on the meridian flip, which is okay. You're going to get through N.I.N.A, you can do an automatic meridian flip. It'll find PHD2 will stop. It'll refine another guide star, and you can keep going. This will typically get you a little bit of a shift, but you can live with it. Where you really don't want is your meridian flip to be right there when the transit is happening. But this kind of shows me the transit duration, and kind of a nice graphic that shows me what I can expect. Okay, so then kind of going down the page further, here's the exoplanet object container. I talked about that earlier. And then here are some steps, triggers that I put in to restore guiding in the event that I lose it. If I have a situation where I have a drift, I'm allowing this, and again, I don't have that great of a polar alignment right now. You might look at that and go, oh my gosh, 96 pixels, that seems like a lot. I hope to be able to tighten this up a lot. But in any event, if I get off by more than 2 arc minutes, I'm going to stop, I'm going to recenter, and then restore guiding. This isn't great, of course, because it means that you're going to lose some of your observation time. So I really do want to fix this, but it does give you a way of pulling things back in so that you don't continue to drift and drift and drift. And then here is just waiting for the observation time, typically an hour before at least an hour before you expect the transit to begin.
Manny, a quick question.
Yes.
You're talking about center after drift. Does it even make sense to dither when doing this since you're not stacking the data?
Good point. Yes. As a matter of fact, I don't think I'm dithering. Hopefully I didn't show a dither there. Yes, that's a good point. I don't dither when we're doing this.
Okay, so you're just accounting for any natural drift that might
Natural
happen.
drift, yeah, which is, it feels like that's drifting more than it should, but yeah, yes, that's what I'm doing. The other,
Manny,
yeah.
while we're stopped here,
Yes.
There are about 6,000 exoplanets, I think was that chart you put up
Yes.
there, right? Okay, and are they all in our galaxy?
I believe the answer is yes.
Pardon? The answer is yes.
Yes, I
Yeah,
think these are all within the Milky Way. Anything that's beyond the Milky Way would be too dim.
Okay, so you wouldn't be working with those. And I think we're caught up in the questions right now.
Okay.
Manny, I have a
last
question
question.
for you.
Yes.
Linda, do another question?
Yeah, but go ahead, Eric.
Okay. We really don't have to worry about sunspots, do we? I mean, I don't know what's the rotation period of the stars, but it's generally in terms of days.
Right.
And while the sunspot is there, it's dimming the star in a reproducible way. So the dimming curve should look completely different if sunspots happen to go there. It should
Yes.
be much more gradual. Where I assume, just from what I've seen, transits are in hours.
That's
usually.
right. That's right. Yeah. So I'm not going to say that you couldn't have an alignment where a sunspot or a dark spot on the star could happen to coincide with a transit. I'm sure that's possible, but it feels like it's kind of not that likely.
Yeah. Okay. Thank you.
And you would say that then if you've got a dimming that lasts a certain amount of time that you've determined, that it's pretty much got to be a planet.
Yes, or
Yeah, okay.
it could be, it could be an eclipsing binary. It could be other things, right? It could be a false positive.
Okay.
But especially for these that we're going for, this TOI is a candidate planet. It's not a confirmed exoplanet, but certainly for the confirmed ones, the false positive should have been ruled out.
Okay. Thank you.
Sure.
Manny, one last question.
Yes.
When you talked about the Swarthmore tool and how you could filter based on what you were capable of, like depth of transit.
Yes.
How do you determine what your equipment is capable of beforehand?
Yeah. So I imagine that there are ways to do this analytically, but honestly, the best way I believe is to try it. Go out and start, crawl, walk, run. Start with something that's a pretty deep transit, and see if you can get there. If you can get a good curve, and then keep getting more and more. I don't know if we want to say aggressive, but keep trying to do dimmer and dimmer ones and see where your system where you can't get a good transit anymore. And of course it depends, right? If you're at a dark site, your star is like, somewhere, way up near the zenith, to where you're not looking through much atmosphere. You're seeing is good. The air is steady. you're going to do better than with the same equipment if you're down in the horizon and you're looking through, you're looking through some light pollution, and you've got a lot of atmospheric scintillation going on. So yeah, it really depends. I have gotten better than 1%, and I think I may have a slide in here on that. But yeah, it really depends. It depends not only on your equipment. It depends on how good are your calibration files. How good is your temperature control? It's a bunch of things. And so that's why it's hard to do, why it's hard analytically, right? Because there are a lot of variables that go into it. But yeah, I would say the best thing to do is get out there and try it. And now that I've done a few of them, I have a pretty good sense of what I can do and what'll be successful. And so I can use that to my advantage when I'm selecting targets.
So start at the easy end of the pool and then work your way into deeper water.
Yes, exactly. Don't jump into the deep end right away.
Deeper water, shallower transits.
Yes.
There you go. So yeah, and if you're like me, there are issues with camera drivers that cause, there's a super annoying thing where the camera will lock up, or N.I.N.A will lose connection with the telescope, and it can be hard to chase things down. Thankfully, there's a little plugin called Connector, which is awesome, which basically, if your equipment disconnects, it reconnects it. So that's if you've not used these and you're having trouble with equipment drivers, I highly recommend these. And then here's just this is just an exposure. You'll notice I'm using, in this case, a 33% region of interest, and I'll talk to you more about why I do that. Okay, wait, let me just make sure that was the last one. Yes. Okay. All right. So you've gotten your transit curve, and maybe this seems like this is out of order a little bit. Okay, well, let me just go in order. So after you've processed your data, which I'm going to go into momentarily, you have a couple of different options after you've collected your data. If you've collected your images, there are a couple of different ways to process that data. So there is what NASA has called Exotic, and this is right through the Exoplanet Watch project, developed by NASA, runs locally or on a Google Colab cloud environment, and it uses data stored on your own Google Drive. So if you're going to do this, highly recommend you set up a separate Google account for your processing, because if you got a camera like mine, you're going to use a lot of data, and the free accounts are 15 gigs is all. So you can, trust me, you can fill this up really fast. So there's a standard version that you use for data that you get from Exoplanet Watch. There's an advanced version that you use for data that you collect with your own setup. So it's fairly simple to use. It's automatically computes and formats your images and your data for upload to the AAVSO. If I've not mentioned it already, AAVSO, the American Association of Variable Star Observers, is the repository. They've graciously provide storage space for the Exoplanet Watch data that's generated by you or NASA. And so there are also online tutorials, which is really a great thing to help you get started with it. There are videos, and I believe there's the user's guide as well. But as I already mentioned this, you can really fill this up in a hurry. And it's not, in my view, all that flexible. And to me, it's kind of opaque. If you don't have a lot of visibility, if it didn't go wrong, if it went wrong, you don't have a whole lot of visibility into what happened. But here's what it looks like. Here's just a couple of screenshots. Maybe it's hard to read, but it basically takes you down through this page. Mount your Google Drive, load Exotic, load your telescope images, identify your target star, run Exotic, and then this will go through and update your output data and upload it to AAVSO, which is really a good thing. Now, the other option is what's called AstroImageJ, also an open source NASA developed tool. This is also what the professional astronomers use. It's pretty well documented. There's a good manual, and there's an excellent introductory video also put together by Patriot Astro. If anybody's familiar with Chad's channel, it's really good. I would caution a little bit that AIJ has made some improvements since he made this video. So there are things that are different. For example, you don't have to select the target stars yourself anymore. Excuse me, the reference stars for differential photometry. But it is still very, very valuable. So a lot more flexibility in choosing your comparison stars, and detrend parameters, which are the things that you use to help basically calibrate your data beyond just your darks, bias, and flats. This allows you to account for the altitude of your star for and just for detrending on an expected curve shape, for example. You don't have to upload the data to the cloud, which is nice, but on the downside, it is a lot more complicated to learn and use. It's taken me a while to get semi-comfortable with it. And there's extra steps required to generate your AAVSO report. You've got to add parameters to the measurement table that comes out of the data. You got to run a macro, etc. But here's an example screenshot of AIJ. And I love this little star, Kelt. I think it's called Kelt 16b. I have it on another chart here, so I'll wait to talk about it. I think it's the next chart. No, it's not. One after this. Okay. Well, here's what you do when you're using AIJ. First of all, you would batch plate solve and stack your images, which are called in the vernacular, in the AIJ vernacular, they are called slices. And so the way I do this, and the way I think you should do it too, is using Astro, which does an amazing job. It's a freeware program, and it will blitz through hundreds of individual images in a matter of maybe a minute or two. And so that then now you've got all of your slices are now plate solved, and then you'll go and do calibration via bias, flats, and darks. You'll then align the stack, and then the ephemeris that ASTAP generates will be used by AIJ to stack your images. And now what you do is called multi-aperture photometry. So on the prior slide where you saw all these individual stars, these are the comparison stars that AIJ has selected. They're approximately the same magnitude as your target, which is this guy. And so these are used, you can use a maximum of 12 of them. And these are going to be used to help detrend your data. In other words, if you're, because of atmospheric scintillation or whatever, your output magnitude is bouncing up and down, in a perfect world, your comparison stars will bounce up and down too. And you can use that, assuming that your comparison stars are actually stable and not changing in their brightness. You can use that data to detrend, to remove that noise from your target star. So then what you'll do is you'll pick for your multi-aperture photometry, you'll pick your target star, and you'll determine an aperture for the star. So in other words, all of the pixels, the photons that are coming from the star and the transiting exoplanet itself. Then you'll have a band here in between, where basically this is sort of the keep out zone. And then outside of this is your background level. So here's your source, okay, and then your background, and then this is sort of a guard band, a dead zone, where we're not using any of that data. And so now, once you run multi-aperture photometry, you'll get a measurements table, and you'll get a bunch of analysis windows, and you'll get your transit curve. And here's what the output looks like. And so here's, I love this star called Kelt 16b, and some of you may recognize this little, or not so little, astronomical object here. Anybody want to hazard a guess? Okay,
Pick me.
it's the Veil Nebula.
Yay.
Yay, it's the Veil. So so that little star is right there. This is just a blow up of the frame. So really cool that I got the Veil Nebula in the same frame. And then here's just here's some information about the telescope and camera, which I've told you about. I used in this case just a Vader luminance filter, 45-second exposures, which I guess I decided I needed to show that twice. And then using the camera at unity or zero gain, 33% region of interest, I collected 340 frames. And here's the data, the detrended data. So you look at that and you go like, oh my gosh, that's pretty noisy. And one of the detrend things that happens here is AIJ goes through and it does a best fit to this curve. And so this is the transit ingress and egress that was predicted by Swarthmore Transit Finder. And in here you can see what I got. So it's, you know, pretty close, I would say. And then in this particular case, you can look and see that this was 0.985, which, what is that? 0.015 or so. So this is actually it's right here. This is the details. So this will show you, where is it? It is about a 1.5%. Oh, here it is. It is a 12.56 parts per thousand transit depth. And so also this is a Jupiter 2.75 mass Jupiter planet. I guess I could have read that. Predicted 11.46 in parts per thousand. I got 12.56. The duration measured and predicted. And then here's the orbital period. I can't remember if this is predicted or measured, but the two would be very close to one another. And I took this back on September 30th. Okay, so here's some other results. I won't go into these in details, but you can kind of look at the transit depths on here. This is a deep one. Okay, this is actually 48, almost 49 parts per thousand, 18.5 parts per thousand, 10.9 parts per thousand, and then here, yeah, okay, this one actually was only, okay, depth, sorry. This is 14 parts per thousand. I'm looking at the wrong thing. Okay, I didn't put in my my under 10 parts per thousand yet, I guess. Okay, here's another plot that you can get. So here's the transit itself, and then each one of these is one of the target stars, or one of the reference stars, the comparison stars. So you can see they're rattling around a little bit. And some of these, you can see there's a little bit of a trail off. So it's kind of interesting. I think this is where my meridian flip happened. That's why there's this gap. And so you can see the ingress and egress. Now this is geocentric Julian date, which is fraction of a day, which is the way that wants to plot. Okay, so once you've now gotten your data collected and you've got the outputs, you don't upload all of your image data to AAVSO. You just upload the outputs, all the measurement files, all your comparison star data. So it's a pretty big spreadsheet, a CSV format, but you don't actually upload, thankfully, your raw imagery because it would be huge. But anyway, when you get to the AAVSO website, you want to set up a free account and get yourself an observer code. And then you would edit your profile to specify your site information, your lat long, the equipment that you're using. And then you can create a report using Exotic, or you can do the AstroImageJ process that I just talked about, where you would complete your transit analysis. You need to add some parameters here to your table. And there's a script to do this. And then you run a macro to generate the proper format to upload this into AAVSO's database. So what have I learned so far? I've been at this, I've done maybe, I don't know, maybe less than 10 exoplanet transits so far. I've tried, I think I've attempted over 20, but have only got about, I think, 10 in the bag. So you can get a transit practically every night. So if it's clear, in all likelihood, there'll be a transit that's available either that night or the next night. So you want to make sure that you can select targets that you can eliminate, that you can image, excuse me, for at least 30 to 60 minutes before and after the transit time. You want to have a nice period on either side where things are not changing, so that you've got stable data. Higher elevation angle, definitely better. You're looking through less atmosphere. You want to filter in Swarthmore Transit Finder for a magnitude and transit depth that you can achieve with your equipment. It takes practice. You're going to need a lot of calibration data. So if you're an AstroImager like I am, almost all the time I'm doing 5-minute subframes. I'm not doing these shorter ones, but what you're going to find is that different stellar magnitudes are going to require different exposures and sensor gain settings. So you're going to find out that this one needs a 45-second integration time. This other one needs 30 seconds. If you use the Exoplanet plugin in N.I.N.A, it'll tell you want 17 seconds. And so guess what? Every one of those individual times, you're going to need a new set of calibration data, at least the darks. And so that's a lot of data. So what I did is set up a sequence in N.I.N.A to automatically step the gain, offset, and region of interest, and to create this set of files. The first time I did this, I forgot to indicate the exposure, gain, and region of interest in the file names. And now it's literally like the adage is picking out the fly crap out of the pepper, right? It's like, here's all these files, which is which, and you can't look at all the individual metadata in every file, in every FITS file. So do yourself a favor and put the gain, you can do this in N.I.N.A, put the exposure, the gain, and the ROI right there in the file names. And I can't stress this enough, disk space is a big deal. If you have a full frame sensor like I do, use a region of interest, because if you use that entire frame, it's going to be, every night is going to be many gigabytes of data. You will fill up your hard disk, trust me. Okay, you want to have a balanced cadence when you're selecting exposure times. If you're less than 30 seconds, first of all, you're going to get a mountain of data, and you're going to be more susceptible to atmospheric scintillation. So that, that twinkling of the stars is going to be more of an issue if you're doing short exposures. So, and also you're going to get a lower signal to noise ratio. So you want to be longer than 30 seconds, I would say, in general, and you'd want to be less than 3 minutes, because otherwise you're going to start reducing your timing accuracy. You really want a couple of data points on that ingress and egress slope. And if you're taking long exposures, you're not going to get very many data points along the slope. So, and you're also going to potentially saturate either your target or your comparison stars. Keep track of the parameters. I use a spreadsheet to do this. And later on, if you get a target star that's about the same same magnitude and altitude as when you've done before, that'll help you a lot in setting up your exposure times. And then develop a workflow and document it. This stuff is complicated, and so I've put together a workflow, if you're using AIJ, that steps you through what you need to do for your analyses. I started with the Patriot Astro video that I talked about before, and I'm constantly, every time I do it, I update that workflow documentation. If anybody's interested in that, I'd be happy to share with you. Get in contact with me. I can share with you my workflow. And then, as I mentioned before, these are the resources that are out there. They are in the description as well, so you don't have to write these down. You can just click on the links. And then finally, if you'd like to get in touch with me, that's my email. And I also have an AstroBin account, and I have a website as well. And it's not .org or .com. It's actually .space, which I think is very cool. So yeah, so that's about it. Anyone have any more questions out there?
I have a question for you.
Sure.
And I say this only because I think we skipped the nut of how you've determined what the magnitude of the star is. I know it. I think multi-aperture photometry you were talking about.
Yes. I could
Tell us how that works. What do you mean? You got comparison stars, but I never heard you explain how they work or whatever it was.
Okay, so first of all, if you go here, oh boy, I hope this doesn't cause me to mess up again. Let's see. All right, so first of all, the magnitude of the star is right there. So when you go to Swarthmore Transit Finder, it tells you all kinds of cool stuff, including the moon angle. Here is the start, end, and midpoint time for your transit. How long is it in hours? This is the time. Here's the elevation, which is good too, right? So you want to know, etc. And this band indicates the uncertainty on the transit. So here's your azimuth, okay, wait, HA at start. Why does this escape me right now? What this means? Oh, hour angle. And then here's your RA and deck, your period, etc. But so to answer your first question, Alex, the magnitude is right there. And then you can get a lot more data here through the Aladdin database. And there's any Exoplanet archive, Simbad, lots of good resources right here that are just one click away. Then in terms of the multi-aperture photometry, in just very briefly, here, the computer is being slow. Give me a moment here. I may have
What was that N.I.N.A plugin again for the Exoplanet?
It's literally called Exoplanets.
Okay.
Yes, very easy to remember.
Okay.
Let me skip forward here. So yeah, so when you do the multi-aperture photometry, these here are all of your comparison stars, and these have been pre-selected by AstroImageJ to be approximately the same magnitude as your target. So this is really all kind of handled within AstroImageJ. It basically goes through and does what's called detrending. So it will look at how the magnitude of these stars changes through your through the stack of images that you have, and it will use that information to correct the your target star. So
okay, so what you're saying is I use one of my comparison stars, and I know it is supposed to be magnitude 12.2, and then I compare it and how bright it looks in my image to my target star, the one that I'm trying to analyze.
yes,
and it gets brighter or dimmer compared at its own rate, whatever that is. And the way you know it's getting brighter and dimmer is that the other one, the comparison star, is not changing, and it is. So it's relative to, okay, so that's the key to how it's done. Okay.
yeah, and actually, typically you're using a lot of comparison stars. So you can see here C12. I'm actually using, well, C13. I'm actually using 12 comparison stars. I don't know why it does this, but the T1 is the target, and then C2 is the first comparison star. That's C11. Yeah, C2 is over here, right here. C2 is the first comparison star. So yeah, your max is 12, and this is some of the secret sauce in AstroImageJ. Thankfully, you don't have to do this detrending. It will do it for you. And then there's so much more. I would say watch the Patriot Astro video before you do anything else, because it's going to take you through this process, and it'll show you a lot of the stuff that the AIJ does for you. And so thankfully you don't have to sit here and do all this stuff by yourself. Once you once you hit the button, AIJ selects these stars for you. It knows which ones are about the right magnitude, and then it will track them frame to frame to frame to frame in your image stack. It does all that for you. So yeah, there's a whole, when I say it's complicated to learn and all that, that's true, but it's hugely powerful and it does a lot of things for you. So yeah, as I say, watch the video, and it can go into a lot more detail than I can here.
Manny, I have a couple of questions.
Sure.
Do you have to use bin 1 or can you use bin 2 on this?
It's recommended. I actually just asked this question myself, and it's recommended that you use bin 1 because you're going to have better spatial precision. Yes, I get that if you bin, you'll get perhaps better signal to noise, but everything that I've read suggests that bin 1 is better. I don't think you can't use bin 2, but what I've decided to do is you know, my way of controlling file size is to go with a region of interest and stay at bin 1.
Yeah, I see that
Just being under an arcsecond of pixel resolution.
Yeah, so that's a good point. I am not, okay, so I'm not under an arcsecond. I think I'm at about, oh shoot, I think I'm about 1.4 or so arcseconds. So when I go and try to sign up for the test follow-on program, one of the things I'll be doing is showing some proof of the pudding to where I'm able to do useful science, even though I don't quite meet the 1 arcsecond per pixel. One of by the way, that brings up a very good point also, especially if you're involved in the test follow-on program. You're going to have situations where you have two stars, you have an exoplanet around a star that is a close binary, or at least there are two that are very close in angular separation on the sky. And if you're binning 2, you're gonna mush those stars together. So that is another reason why you want to bin 1.
Yeah, you're using the entire field of view, it looks like, unless this is a region of interest. So I'm thinking bin 2, yeah, bin 2 will give you 1/4 of the file size, and if you could do it, that would be nice.
Yes.
The other comment is this is not really an all year round activity. I mean, it's really best when the Milky Way is up in your area. I mean, this is a spring, summer, fall activity.
That's
more
a
than
good
winter.
question. I believe there have been a fair number. I know Tess is looking at, I think, a region of sky in Cygnus. Is that right? Does anybody know
That sounds right. Yeah.
Yeah, and so it's looking at a square region within Cygnus. So you're right. I believe there are exoplanet candidates that are available in the winter. That's a good point. I could flip on the Swarthmore Transit Finder. I don't know that I want to.
No, I'm just thinking naturally, you know, in our astrophotography, if you're going to image in the Milky Way, it's always nice.
Yes.
No, there should be some number that's out, you know, in the section of the Milky Way that's up in the wintertime, but it will be proportionally less because you're looking at less galaxy.
Yes.
On the other hand, how many do you need?
Well, yeah, I guess the question is how ambitious are you, right? If you're really diving into this thing with both feet, and it's like, I want to image every night that it's clear. Yeah, I mean, go for it. You can certainly. It's an embarrassment of riches. There are lots and lots and lots of candidates out there, and if
you can stop sharing if you want.
Oh, sure.
Yeah.
Yeah, I could do that.
I suspect the reason Eric was asking about binning, because I think your native image scale is like 0.3 or something like that.
Yeah, I mean, you have to be aware of whether you're oversampled or undersampled. And
yes,
I mean, I guess if binning will take you to 0.6 or 0.8 or 1 arcsecond, then you're probably still good.
Yeah, that's a good point. Yes, if you can bin and still get under that 1 arcsecond, then maybe you're fine. Yeah, the RASA, of course, is very wide field, and so if you were starting from day one, going, I want to build a rig to do exoplanet imaging, you would probably not choose what I have. But I started out with astrophotography, and so yeah, so that's why I have what I have.
By the way, I think we're all kind of obsessed, and yes, we do want to image every night that it's clear.
Definitely true.
Oh, I mean, that's great. Great presentation. Thanks very much, Manny. You know, again, I always say it. There's always something to learn that's new. Have we missed any questions, Alex?
Yeah. Well, it's a comment that I think we should pay attention to, and Manny can't see it. So Naveen Ravindar says, for aperture photometry, you should never bend, and it's actually better to lean on the oversampled side. Aperture photometry sums the counts of the entire star area, so bending provides no benefit, he says. And he also says that you should measure it in, oh, no, he just says you get a better full width half max. And what is the minimum full width half max for good photometry? Manny, that's what the question came down to. What is the minimum full width half max for good photometry?
Okay, boy, that is a good question. That's a good question. I mean, if you look at my data, you're looking at I'm not going to share again, but you know, I'm down in probably, I'm going to say a couple 3 arc seconds is where I am, but I think you want to be, you know, you want to be as good as you can, right? So
Okay.
thumbs
And there we
out.
go. This is just some more comments. That one was from Astronomally.
Oh no, I was just making a comment. Did we ask the question about 12-bit versus 16-bit? A little higher up. There's a question from
I didn't see that. Sorry.
Narasim. Sorry. What is the real life difference between a 12-bit and a 16-bit camera? Maybe here as it applies to photometry.
yeah, so I think this sort of is sort of the same answer as you would have for astrophotography, right? So my camera is 16 bits, and you know, definitely the better, you know, at some point you get into the noise, in which case then it doesn't matter. The extra pixels, extra ADU counts don't really help you. But I would say, you know, can you do it with 12 bits? I would say probably yes, but you would need, I think you'd be dealing with brighter stars and deeper transits.
He also asked if he wants to find undiscovered exoplanets, so looking for variability in whatever other images he's taking. Is there a workflow for that?
Yeah, so I would answer the question the same way that Brian answered it a couple of weeks ago, which is that's really hard because you've got, you know, you have satellites up there that are above the atmosphere that are able to see things much, much dimmer and with much more precision than we can here on the ground with our amateur equipment. And, you know, they've found 6,000 or so exoplanets so far. So I would encourage people just to say that that's hard. Finding new undiscovered exoplanets is very hard. And so I think if you're really ambitious and you say, I really want to get on the leading edge of this thing, to me, the way to do that is to get with the test follow-on program, get accepted into that program and start helping to weed out those false positives and confirm candidate exoplanets as real exoplanets. And the cool thing, I think I touched on this before, is that as you are looking at these transits, if the transits move around over time, that's indicative of a potentially a second exoplanet orbiting the same star. And so that's a new discovery. And by the way, another thing I didn't mention is that if you are, I think it's true with Exoplanet Watch, it's definitely true with Test Follow-On Program. If papers are written using data that you collected, your name goes on the paper. So if that's a if that's a validation for you to be quoted in a scientific paper, I think that's pretty cool. That's another kind of perk for being able to contribute data. Is to
Actually, there are several ways you can get on science papers, but as a scientist, I mean, that is the rule. If you contribute to the science, your name goes on the paper, whether you little bit of data or whether you're the lead author. And as far as discovering something new, a few years back, I decided that I was looking at all my luminosity. Anytime I saw an asteroid, I was going to search it out to say, okay, I may have discovered that. After a few dozen, I realized they've all been discovered.
Yes.
So I wasn't going to discover any new asteroids.
So I had a question regarding your choice of gain and versus exposure time. So I know you want to maximize your full well depth and use as low a gain as you practically can. And so my guess is that you only want to raise your gain if you need to keep your exposure time short enough to not be excessive for the length of compared to the length of the transit and the length of the ingress and egress times.
That's correct.
That a good summary?
Yes. Yeah. And also, the other thing I'm doing is so far I've only used gain 0 and gain 125 because I don't want to like start adding a bunch of different gain values on top of everything else, right? Just think about your calibration library, folks, when you start this, because it's non-trivial.
Listen, I think we've kind of come to the end. We're running a little bit long, but thank you very much. Great presentation, very well organized, and we always learn something. And for all of you out there, come back on the 18th, and we're going to have a very interesting presentation. Let me remind you of the calendar. Warren Keller, Stretching and Pix Insight. I'm sure Warren's going to talk about that new
I think he's talking about the new
routine.
tools. Yeah.
Yeah, the new. Oh, by the way, if you haven't used that new tool, it is really a cool tool.
I have to go double check, but I think he was going to cover Verilux and multiscale adaptive stretch, whatever that new one is, possibly some other ones. I got to go check what he sent me, but yeah, I think some of the new tools.
All right, so everyone else, good night. We'll see you in a couple of weeks. And Manny, if you want to hang in there, we usually continue for a little bit.
Sure.
Hang on.
All right. Good night, everyone.
Take us out. One sec, and here we go.